So we're going to be focusing on what is new in the newest versions of Inventor and Fusion 360. Just so that you know, Inventor, if you are not on 2022, I recommend upgrading to that. And if you are using Inventor 2022, make sure you've installed all of the most recent updates so that you have access to all of these new tools. If you're using Fusion 360, Fusion 360 will automatically update. So you'll see a status bar in the top right corner when you next open Fusion 360. These updates are probably already installed in Fusion, but if they are not, reach out to your IMAGINiT account manager or your reseller, and they can help you get that squared away. So about us a little bit, it's going to be me, myself, Ed Gillman, and then Nate Cassou doing the presentation today. Both of us are mechanical engineers by trade. I have some experience in aerospace, product development, advanced manufacturing. I've bounced around several industries and gathered a broad skill set. At IMAGINiT, I handle the majority of our simulation business, so I help out providing consulting and training for Nastran and CFD. I also assist in the CAM, advanced CAM, and generative design with Fusion 360 worlds. I'm based in Denver, Colorado. Got Nate Cassou here today as well. He also has a bunch of experience in manufacturing, and he also has direct experience as a professional machinist for aerospace. So he's done some really complex machining as well as design work as an engineer. And he's based out in Seattle. A little bit about IMAGINiT Technologies. If you don't know about us already or you're not already working with us, we are an Autodesk Platinum reseller. We're one of Autodesk's largest services partners, which means we have a really large staff with expertise in almost every single Autodesk software that's available. We've been doing this for a long time. The company's been doing this for over 40 years. The advantage of working with IMAGINiT as a reseller is we have a really large team. So we have industry knowledge from just about everywhere. We also have a dedicated support team. So if you do have an issue with your software or you need assistance getting something set up or troubleshooting something, we have a dedicated support team that's what they do all day. They've probably seen that issue before and they can get you squared away in no time. We also have a large number of training facilities, as well as mobile labs and online labs. So if you need training, you can do that in person in one of our facilities. We can bring the labs to you and come on site with computers and training resources. We also have online labs. So if you want to do all of your training remotely, which has kind of become the norm with COVID, we have the ability to do that as well. So large company, lots of flexibility, and we're here to help you. If you have a problem, we're here to solve it. So we have the right experience and the right processes to get your problem figured out. We also have the best software available to you and the correct knowledge base to get you trained. Overall, we can help you do things like reduce costs. Maybe you want to switch from a existing software to something that's going to be at a lower cost. We can do that. Improve the quality of your designs. Maybe you want to do things differently or in a more organized fashion. Our experts can help you get set up and get things ironed out and smoothed out to increase your productivity, profitability. You want to have a staff that's highly trained and also on the same page, and we can help do that. Some of the services we provide, anything from BIM and CAD management all the way through CAM, manufacturing. If you've got a new CNC machine and you need assistance programming that, we have the experts for that. If you want to run some stress analysis, maybe you want to improve one of your existing structures, we have FEA simulation experts as well as CFD experts in-house. Data management, if you want to get a vault set up and maybe start doing some product data management. If you don't have someone in-house that can help get that set up, we have experts that can come on site and do those implementation services. We will do that turnkey, so as soon as we leave, you'll have the correct training and resources set up to be using the software from day one. One thing to note, we also have a software development team. So if there's something that Inventor, maybe it doesn't do and you wish there was more automation built into your software, we have a full software development team that can actually build out custom applications for you and custom plugins for Inventor, AutoCAD, Revit, things like that. So we have a full software development team as well. and we can assist with just about any project that comes through. So enough about IMAGINiT. Let's get into the webcast here, and we're going to do some live demos as well as some explanations for you today. This should be an exciting one. I really like the new tools that have been added into Fusion and Inventor recently. So we're going to focus on 4 of the improvements that we found to be the most useful. There are more improvements available as well. If you search online, you'll see there's a large list of new features being added every month or two, especially to Fusion 360. Today, we're going to focus on Fusion 360 machine simulation. So anyone that's using the CAM environment has been asking for this for some time. The machine simulation within Fusion 360 lets us actually visualize machine motion, as well as combine that with fixturing and tooling to improve the safety as well as the efficiency of our simulations. Generative Design has added fluid path generative design, which I'll be discussing in a moment here. That allows you to actually visualize and identify fluid paths within your design, and you can reduce the amount of material being used and the pressure drop can be improved. Fusion 360 and Inventor interoperability. So there's a new Send to Fusion 360 tool in Inventor that makes using the 2 softwares together much easier. And then we'll be looking at the Inventor Make Components tool and the enhancements made to that for surface and solid modeling. So with that, I'm going to have Nate kick off the rest of the PowerPoint here and take us into the demo.
Right, thank you, Ed. I'll go ahead and kick this off here. Show my presentation. So I want to start first with Fusion 360's machine simulation for NC programs. This is a new feature with Fusion 360, and it goes along with the already built-in simulation we have for toolpaths and CNC setups and machining within Fusion. This is, like Ed said, this has been a thing that they're trying to push for some time now. A lot of higher-end CAM programs have built-in simulation because, you know, we're dealing with a lot of expensive equipment, a lot of expensive tooling, and expensive parts, maybe one-off parts that require a lot of movement and kinematics to the machine. And any close calls with the machining can be quite a costly mistake. So we want to make sure that we can look at the machining simulation and get a good verification on that. So the machining simulation within Fusion is really quite simple, but it just allows a lot of usability and a lot of control over how you want to set up your machine before you run an actual machine simulation. So a lot like fixturing, if you ever used fixturing and to run a CNC simulation in Fusion, it uses downloaded 3D files. Okay, so we can actually use files that are not only built in within Fusion for a lot of common CNC machinery like Haas and Tormach and Heidenhain. So we can download those models, but these models are have built-in kinematics that we can adjust to whatever the supplier's requirements are and the specs of it. So not only that, if we have kind of an off-brand machine, we can actually edit the kinematics and build our own machine right there within the software. Also, in the machine simulation, we have the ability to run the machine builder, so we can configure if we have a multi-axis machine, and we have a machine that maybe is a 3-axis, but we want to add multi-axis to it. We have the ability to set that machine up manually in the machine builder. And lastly, with the simplified models, we can also go in and strip out parts from the model just to get a better visual when we run the program. Okay, so I'll go ahead and share my screen here. Okay, so here I've got a part. This is a multi-axis part that I want to run some 5-axis simultaneous machining on. And I can certainly run this with the basic simulation and get a good profile and verification. But let's look at the machine simulation. So first, what we can do is we can go into our setup. So under setup, we can open this up, and we now have this option up here called machine. And really, this option was to, again, allow us to have more functionality when we simulate to priorly to post-processing, set up a lot of the kinematics and machine definition. And now what Autodesk has done is they've loaded all these 3D models inside of Fusion that we can use. Okay, so I'm going to go ahead and go edit. Pardon me, I'm going to go select. That's the one I wanted to use. And you'll notice that brings up my new machine library. Okay, so I can go in here, and on the left-hand side, you can see that we have several different links where we can go and find our machines. We have a Fusion 360 library. So if I scroll through these, you can see that we have a lot of different generic configurations already given to us by Autodesk. So right here, we can just kind of scroll through this, and if we're familiar with how CNC machines work, they come in a lot of different configurations, from 3-axis all the way up to 5-axis, configurations that have multi-axis only on the head, on the table, on gantries. Okay, so as we scroll through here, you might notice some of these machines that that might match up with what you have at your shops. So right here, we've got, if we keep scrolling down, we have all of our Autodesk generic tables that we can use. And when we're ever verifying a simulated, when we ever want to simulate a program, it may be useful just to grab one of these generic Autodesk 3-axis or one of these generic machines to then bring into the machine builder and modify. But we keep scrolling down here, we'll notice some more common machines like Haas and Herco. Okay. So we have some Mazak. So, and a lot of these machines are multi-axis because machining simulation, again, if you're doing any kind of multi-axis stuff, it can be quite tricky. So we want to make sure that we can get a good simulation on that. So as we scroll through here, we can choose one of these machines to do our simulation on. If we've already built a 3D model of a machine and we want to import it in, we can save it on our local files. These are the machines that I've used priorly within machine simulation, so I can, as I use the machines and take it from the Fusion 360 library, I can put it right here and save it locally. Okay, and this just saves conveniently to your local, so you can always use ones that you're most commonly familiar with. Okay, so let's say I chose one of these machines, like this Haas UMC 750, which I've already loaded right here into my setup. Everything else is the same. We choose our milling operation types. We choose our WCS direction, our model, our fixturing. And then we have this new tab here called Part Position. Okay, once we set up our machine, if I scroll out, you'll notice there's the translucent or transparent 3D model of our UMC 50. But the neat thing is that now I have almost like a built-in movement tool right here, so that I have a lot more control over where I want to put this fixture. Okay, so we have just the generic or the stock Haas 750 table, and if I wanted to put multiple fixtures on the table, or maybe it was offset higher, we can always do that. So we just have a lot of control over where we want to put this fixture. And just like the movement tool when you're 3D modeling, or the movement and positioning tool that's built into Fusion, I can grab these wheels and move this anywhere I want to move it. Okay? And we can also put in some hard values in here if we actually know where this fixture sits on our machine. Okay. Scroll back out. Now I have this 3+2 operation that I want to run and a five-axis simultaneous operation I'd like to run. So I'll just give you a visual of what that looks like. Okay, so I'm going to go ahead and go to my milling, simulate this process. Okay, we can see we've got our stock in there and our first tool, which is our big facing tool. Yeah, as it's running, you'll notice that the way we've set up this machine and the kinematics, which I'll show you here in a second. Okay, we can see our C-axis moving. And as we skip forward, we can notice the kinematics of the machine automatically adjusting to the toolpath. And if I pause it here, I can get a really good visual of how this thing is going to look when it's machining, right? Because remember, these models all come from the actual machine itself, so they are accurate to the actual machine. Okay, so we're just running a simple 3+2 operation, and then you can see right there our tilt angle when we want to come and do some of this harder to reach areas. Okay, I'm going to close that out. Now, if we wanted to get more control over the kinematics of the machine, what we can do is come over to our utilities. We can go to our machine builder. Now, what I did was I went ahead and opened up this model in a separate window, and you can see that it's just like any other Fusion 360 model. We've got our base, we've just got our solid bodies here. And the neat thing about this is I can go into these models, and if I want more clarity to look at my model as it's simulating, I can hide components. Okay, so I can hide the whole enclosure if I actually want to if I'm not really concerned about hitting the enclosure itself. It just gives me just more of a better visibility if I want to look at the part and how it's running. Okay. I'm going to come over to utilities, and we have this new tool up here called Machine Builder. And this is where I can come in and do any kind of fine tuning to the kinematics of the machine. So I can certainly come in here and select a different machine. So that reopens my machine library if I want to choose a different machine to modify. And then right here, I've got this edit machine configuration. So again, this is also built into the setup when we go to add our machine into the milling setup. And we can just give the machine some information. We can give it a description. What is it? Its control, dimensions. So we can give it a width, height. So what are the actual dimensions of the machine? What are its capabilities? How many tools it can hold? Its workpiece capability. So what's the largest size of workpiece it can handle? And then we have our kinematics. So this one's pretty interesting. Kinematics, this is the armature and the movement of the machine. Okay, so if I go into X linear, so you'll notice that these are default values. Okay, so this actually comes from the machine itself and the model, and most likely from Haas. So it gives us our default home position, and we can enter in a lot of these values manually. So if we want to give a min and max for our linear x-axis, we can do that. If our linear axis, we want our main linear axis, we can change right here. Y linear, Z linear, spindle. Okay, so what's our max spindle speed? That we can get a lot of this information from the supplier as well. And anytime we want to activate an orientation on our machine, we can use that with zeros and ones right here. So one being the activated spindle axis. Okay, so that being Z. And then if we have multi-axis set up on our machine, we can add rotary axes to it. So a B, C, and different configurations. So right now, what I have right here is I have my X, Y, and Z all on the spindle, okay? And then I have my B, C, my B rotary and my C rotary linked to the table. And so on each rotary axis, I can come in and either change the coordinate, maybe it's an A axis, give it a home position, max feed rates. And I can also come down here and, for instance, this B axis, I can change the range of it. Okay, so right here I have a minus 110 to 110 degrees, and then that's where I can come over here to my movements, and I can actually see what that's going to look like. So on this B axis, you'll notice I can get a good manual view of the range I put in. So we can test out these limits before we, or excuse me, after we make our edits to the machine. Some other functionality we have, we can move components around. So if we don't like where this table is sitting or if it's an offset, we can do that as well. We can also set up our machine model if we want to in a different configuration. Okay, I'm going to switch over to our next item. I'd like to discuss a little bit about the interoperability between Inventor and Fusion. So, for the longest time, we've not had a lot of interactability between Inventor and Fusion. Obviously, Fusion and Inventor can both import files, but we lose a lot of the associative features when we're importing and exporting between the two softwares. Well, now with 2022, we can send parts from Inventor into Fusion. The reason for that is we're finding that people really like a lot of the tools in Fusion, but maybe they like modeling in Inventor. Fusion does offer things like manufacturing extensions or machining extensions in the extensions portion of CNC machining within Fusion. It just gives you a lot more functionality and tools to work with for multi-axis and different machining strategies, but also other manufacturing strategies as well, like generative design, and Fusion has a pretty good simulation package as well. So that's the reason why we're doing this interoperability. Plus, if teams are accustomed to using Fusion, like Fusion Teams, this makes it a lot easier for them to share files. Okay, so we can send files from Inventor into Fusion 360 from the Environments tab in Fusion. We can, and obviously, like I said, we can obviously open up IPT files directly from Inventor in Fusion, and just by importing. To open a file in Fusion, you have to either be on a Fusion team or have been invited to a Fusion team to view the file, because again, that's how a lot of the file management works within Fusion. And then another workflow we have is the AnyCAD workflow. Okay, so we can open up 360 files in Inventor and parts and assembly. So this is just, again, more of a simple import-export between the two softwares. And like I said before, we can use the tools in Fusion with Inventor models, just to our advantage to have more options. So I'm going to go ahead and share my screen. Okay, so we've got this Inventor part here. And what I'm going to do is I'm going to come here to my environments. I'm going to go to the Send to Fusion 360 button. Okay. Ask us to save the file. Yes. And then we get this wizard over here. It's very simple. It just asks us to send the file. And if we want to learn more about this interoperability, we have that button down here. I'm going to go continue. We get a downloading screen. I already have this part loaded into Inventor, or excuse me, Fusion. I'm going to go ahead and upload a new version. Okay, it uploaded successfully. I'm going to go back to Fusion. I'm going to go into my folder where I directed the import. And there it is. There's my new part. I'm going to go ahead and open that up. And you'll notice it says IPT right there and the date on which it was imported. Give this a second here. Okay, there's our imported part. And now we can use this to create toolpaths from, doing design and simulation. One thing I'd like to show as well is some of the changes that we can do from Inventor into Fusion. So again, we can't really import associated features like extrudes and cuts and have all those sketches and dimensions to link between the two. But what we can do is I can make a change here in Inventor. So I'm going to go ahead and collapse this down. And if I wanted to make a change to this, let's just say I wanted to put maybe a set of holes on this side. So I'm going to go ahead and create a sketch on this. And I'm just going to create just a simple hole. Go ahead and create like a point here. Be a couple of points. And say finish. And I'm going to go to my 3D model, create a hole. Doesn't look very good, but I want to show you how we can make these changes. So I put these holes right in here around this, just arrayed them around that surface. And now what I want to do is I'm going to go to my environments, send to Fusion 360. Yes, I want to save it. I'm going to go to continue. It says a file with the same name exists in this location. A new version will be uploaded in Fusion Team. I'm going to go ahead and click that same part, upload the new version. Let's try that one more time. Okay, there we go. Close that. Go back to Fusion. And then we get this warning right here, component is out of date. And you'll notice that we don't have those holes right here, but all we have to do is simply go update. And there we have our holes. Okay, so we do have some functionality between changing features and some associated features. If we wanted to edit some of these features from Inventor into Fusion, we're still only limited with using. I would have to come back in here to Inventor and actually change the parameters of this hole and then update it right here in Fusion. If we want to do any kind of editing here in Fusion, we're still only limited to direct edit, like press and pull. Okay. Another thing is that, which I've already tested out, we can't, if we had any CAM tool paths on here, we don't have the functionality yet to update the toolpath. So if we already had a toolpath on here and we changed, say, the diameter of that surface, it wouldn't update. But hopefully they can get that functionality at some point in the future. All right, I'm going to go ahead and pass this back over to Ed, and thanks for joining.
All right, thanks, Nate. So I'm going to wrap up the webcast with a couple more topics here. I'm going to go through explaining generative design with the fluid tool, as well as make components with Inventor. So this new tool to generative design, if anyone's used generative design, they know that it's primarily for taking a stress analysis result and using it to guide the design of a structural component using either 2.5 or 3-axis milling. You can do 5-axis or 3-axis additive. The new tool allows us to actually use a CFD-based functionality and simulate the fluid path through a design. You can then optimize the geometry to minimize the pressure drop based on the geometry. So what it'll do is you'll set your inlet velocity or your inlet volume flow rate. So let's say you have 50 CFM at the inlet. You can then set your outlets to be a zero pressure condition so the fluid can flow through. The solver will then determine the best fluid path to minimize pressure drop while reducing the amount of material being used. So this allows you to generate a part that is going to be less material, so it'll be lighter weight, less waste. You will also improve your energy efficiency, so the amount of material required to kind of generate that proper pressure drop in your system. So this is a great way to kind of look at a preliminary design where you know where your inlet and outlet is. Anything in between is still kind of unknown, or you want to optimize an existing design. It's going to take whatever you give it, and then it's going to cut it down into a more efficient design. So same process as regular generative design, but with a fluid boundary condition as opposed to structural. The Inventor Make Components tool allows you to take a part file and break it up into an assembly. So if you've created a part that has a multi-body scenario, so you've created multiple solid bodies and you want to then convert it to an assembly, Make Components has been around for quite a while. The new functionality is you can now select surface bodies. You were not able to do that in the past. It's something that I've tried to do and was never able to do it. So now you can just select a surface or a solid body. They can be visible or invisible, so you can choose anything from either of those two folders. It'll then convert those into an assembly. These surface bodies will be their own part file. This is extremely useful if you're doing any kind of plastic part design, which is what I'll show you. It also can be used for finite element analysis if you're taking an assembly and you're creating some shell elements. You might create a surface model. You can then export it into an assembly and run your stress analysis on the assembly with those surfaces, as opposed to being limited to just a part file. So there are some advantages to that workflow as well. So looking at the Inventor side of things first, this is a hair dryer that I'm working on designing. So this is going to be a plastic part primarily. I want to design a over-molded rubber grip for this handle. I don't want it to be too slippery and fall into someone's hand and then break. So this handle, that's going to be really difficult for me to do as a separate part file because I'm going to need to take a lot of dimensions. And this is a pretty complex sweep feature. I really don't want to design this separately. So this is going to be something that I need to reference the part file directly. One of the easiest ways to create plastic parts is with a surface and where you actually go and thicken it into the appropriate plastic thickness later. So to do that, I'm going to just first create my surfaces. I'm going to do a thicken offset on this. I'm going to offset it 2 millimeters outward. And I'll just go ahead and extend it down a little bit, maybe another 2 millimeters. And then I'm going to do a surface patch on the bottom. And then I'm going to go ahead and stitch these together. Actually, I'm going to do a quick trim too. We're going to trim it at the top so that it doesn't overlap, something like that. And then I'll go ahead and stitch together these bodies. So some basic surface modeling. I'm just creating a shell surface here, and it takes into account the complex sweep on the bottom. So I don't have to spend a lot of time designing this if I'm just offsetting it and creating a grip. This is a really quick way to do that, and I can really easily adjust the offset and the thickness here. So next step is, well, now I'm stuck in a part file. I need to break these up into separate components for an assembly for my bill of materials and my drawing and everything like that. So what I'm going to do is go over to Make Components. The new tool here allows me to choose the solid body, but also now I can select surfaces. So in 2022, you'll be able to do this. In 2021, you will not. So it's a new feature. I'm going to rename my assembly as hairdryer. I'm not going to really rename these at the moment. I can rename them later. I'm going to click Apply. And I'm going to go over to my assembly now, and you'll notice there's the part, the actual hairdryer body, and then my surface here has been created as a separate part file. So it's now an assembly file, a .iam. I can then work on these components individually. So now I could go over to this part. I'm actually going to open this. You'll notice it's an entirely separate part file now. I've got my surface in here, looks good. I'm going to go ahead and do my thicken offset now. So I'm going to go ahead and thicken both of these faces inward. I'm going to make them, let's just say 1 millimeter thick for now. Click OK. And now I'm going to take my surface and I'm going to hide it. So I've just got this 1 millimeter thick overmolded rubber grip here. Looks really good. That's going to be easy. I mean, my design is already pretty much done. I'll just go back to my assembly and update it. And now I've got this rubber grip here. My hairdryer, I can verify that everything is cleared with section view through the middle, like that. And I can then see that I've got the internal body and then my overmolded grip with some clearance all the way around. Maybe I leave a little bit of room for tolerances, but now I've got those two part files designed. And this makes it extremely easy to modify because I can go into the part file and let's say I was changing the shape of my grip. I can go back to that sweep feature. I'm going to change the scaling so it changes the shape of that feature. It updates all the way down. I can go back to my surface part here, update this. So it changes the shape of my grip. And then I'll go back to the assembly, I'll update that, and it changes that to match. So now I can make changes to the hairdryer and the grip will update, as well as now the actual assembly will update and I have a completely associative part. So it makes plastic part design really easy and it maintains that associativity that people have been asking for a long time. And all you have to do is just create a simple surface, make components, and then you've got a really nice associative plastic part or rubber part that you can work with. So that's one of my favorite tools in the new updates for Inventor. And now let me just show you to wrap things up here, our generative fluids. So this is Fusion 360. This is the generative design environment. We've got our body here. What this is, if I hide a couple components, is basically I have an inlet on the left side here, an outlet on the other side, and then the internal void here. This body that I'm going to hide represents the current design, so my current fluid boundary. Internally, you'll see I have this cage and poppet that I'm using for a valve. So I have some obstructions in the way of the fluid. This represents my existing fluid boundary, so the current design or what I'm expecting the volume to look like. And then the bodies at these sides are my inlet and outlet. One thing you'll notice is there is a separate body in here. So this body is broken up from this one because when you do a generative design fluid, your inlet and your outlet need to be a separate volume from the fluid geometry that already exists. So that's why these are two separate bodies. Same with the outlet. You'll also notice there's this ring that goes around the inlet body. That represents a what I would call like a flange. What this does is it keeps all of the fluid focused on the internal inlet volume. It doesn't allow for the generative design tool to expand the path of the fluid outside of that inlet. And that sometimes creates like what they call a mushroom shape. You have to have these rings around the inlet or the solver might have trouble converging on a result, or you'll get a fluid path that doesn't really make a lot of sense at that inlet. So to set something like this up, basically what you have to do is first choose your preserved geometry. So what geometry do you want to maintain? Basically what geometry is critical. It cannot be removed. Well, you need at least somewhere for the fluid to enter and exit your design. So that's going to be my preserve. That will be the inlet and the outlet. So I'm going to select those two as my preserved geometry, they'll turn green. I'm going to choose my existing obstacles. So where do I have obstacles the fluid needs to navigate around? Well, that's going to be the cage and poppet, and it's going to be the flanges around my, or the walls around my inlet and outlet. So I'll do an obstacle geometry. That's going to be this guy, cage, poppet, and then this volume here. Something like that. And then lastly, after you do that, what you can do is you can take the starting shape shown here. This is going to be my existing volume. That's going to be my starting shape that the fluid will start with, and then it will remove material from that. So my starting shape will be this body here. So now I know where my inlet and my outlet are, what my existing volume looks like, and any obstructions that might come into play. So have one more obstacle, which is going to be this guy here. This represents just a segment that forces the fluid around this center volume, so that's also going to be an obstacle. So now this thing's ready to solve. Basically, I have all my obstacles, my existing geometry, my inlet, my outlet. Last thing I need to do is give it a design condition. So I'm going to supply an inlet and an outlet. So first, I'm going to select my outlet. I'm going to give it a pressure of 0, so 0 psi. That allows fluid to flow through. So I'll be able to calculate where the pressure drop will occur. And then I'm going to apply a volume flow rate to the inlet. Let's do a unit of, let's maybe do gallons per minute. Let's say 50 gallons per minute. Click OK. So the fluid will come in at 50 gallons per minute. It'll exit out of the outlet at 0 pressure. And the solver will then identify where the fluid goes and where it can remove material to maintain and minimize the pressure drop while reducing the volume. So what you can do is set your design criteria objectives. And you can do a percentage of the volume. So if you say 25% of design volume, it will minimize the pressure drop while trying to reduce the total volume by 25%. So it gives you a target volume in cubic inches. If I wanted to do 50%, it'll then update that target volume as well. So once you're ready to solve, you'll click on generate. What it'll do is it'll take this model and it'll then build out your outcomes. Outcomes are going to look something like this. So I have this fluid path here that I generated earlier. If I open up my fluid path, it's going to show me a 3D mesh of what this fluid path is going to look like. So you can see my inlet, my outlet remain the same, and then the fluid is flowing around this internal cage. And you can see where that flow goes and where it's trying to reduce material. You can see that ball shape. So if I show my starting shape, you can see that it removed a lot of that material. It's kind of focused it towards the center. I definitely don't need all of this external volume. I can probably just shrink down that sphere. I may not need to make too complex of a shape, but I could definitely shrink the overall diameter of that sphere to more closely match the shape that it's giving me. I can also look at my pressure. So this shows the actual pressure, and you can see there's a total pressure drop of about 0.9, almost 1 psi. And you can see what the pressure is on the internal void here, right around half a psi of pressure around that cage. And then I can look at my actual flow line. So this shows traces of each particle. You can see them flowing through, and you can see where there's a lot of velocity increase through the center of that cage. And you can see there's a little bit of recirculation in the lower chamber of that volume as well. So this is going to show me the actual path that it's going to take, a preview of what the design will look like, and I can overlay it with my existing shape to kind of see the differences and where I can make improvements. Once you feel good about what you've generated, you can then use this create tool to actually create a design or a mesh from the outcome. Creating a design from the outcome will basically create a solid model from this actual shape here. This probably isn't production ready. Looking at it, there's a lot of varying thickness, some complex curves in there. What we can do is you can use it to guide your design. It doesn't need to be directly converted. Unless you're doing an additive process, this is going to be really hard to create with standard CNC tools or even plastic parts. So you'll probably want to simplify it and use this more of a design guide as opposed to a direct model. But this will give you some really good insight into where you can improve your valve or improve your chamber that you're working on, and then you can continue to work on the design from there. So really just the highlights of these softwares and what's come out recently. Autodesk is always doing some really neat things, adding some neat tools to the existing software. So if you have any questions, please throw them into the questions box now or the chat, and we'll get those answered. And I really appreciate everyone for taking the time to sit down with us today and learn a little bit more.